Good afternoon, everyone. So welcome to my YouTube channel, Math Circle. So today we are going to see third lecture on subgroups. Okay. In this lecture, we also find necessary and sufficient condition for a non-empty subset of a group to be a group. Okay. Let's see how we'll start this lecture. So what are results? So you can say corollary or you can say theorem. It is up to you. So we are calling it theorem. Okay. Let G be a group and H be a non-empty subset of G. Okay. Then H is a subgroup of G if and only if A B inverse belongs to H or all A B belongs to H. Okay. So let's prove it. So first assume that H is a subgroup of G. Okay. Then so let A and B belongs to G. Okay. Since so AB belongs to H. Since H is a group, this implies B inverse so this implies B inverse belongs to H by existence of inverse in H. Okay. Now A belongs to H, B inverse belongs to H. So this implies AB inverse belongs to H by closure property in H. Okay. So what we have? We have AB inverse belongs to H for all AB belongs to H. So direction is proved. Okay. Now conversely assume that H is a subgroup. Conversely assume that AB inverse belongs to H for all AB belongs to H. Okay. Now B inverse belongs to H for all AB belongs to H. Okay. Now taking B is equal to A, we get what we get. Taking B is equal to A, we get what we get. A inverse belongs to H. But A inverse is nothing but E. Okay. So this implies E belongs to H. Okay. So identity element of G belongs to, okay, in H. Now A B inverse belongs to H. Okay. For all A B belongs to H. So now I'm taking A is equal to E. So taking A is equal to E, we get E B inverse belongs to H. For all B belongs to H. So this implies, what is this? So this is identity. Okay. So how we can write? So this implies, so we can write B inverse for all B belongs to H. Or we can now write A inverse belongs to H for all A belongs to H. The meaning is same. We are replacing just by A. Okay. It does not affect anything. We are changing just a symbol. Okay. Okay. Now A B inverse belongs to H and B inverse belongs to H for all A B belongs to H. Okay. So this implies, so I can take, because okay. So what I will do? I will take replacing B by B inverse. So AB inverse belongs to H. Okay. So what I will do? So how can I write this statement? So I want to write this statement in a different way. So AB inverse belongs to H and B inverse belongs to H. So I can write this statement. AB inverse belongs to H for all A, okay, B inverse belongs to H. Okay. The meaning is same because B belongs to H implies B inverse belongs to H. Okay. So I can, okay. So this is the meaning. Now I can, because G is a group, because B inverse is B. So in place of B inverse, we can replacing B inverse by B. Okay. So I am taking B inverse belongs to H for all A B inverse belongs to H. So this implies A B belongs to H for all A, and what is this now? B. Okay. So what we have? We have A B belongs to H and A inverse belongs to H for all A B belongs to H. Okay. Now by previous theorem, by subgroups, lecture 2, we have H is a subgroup of G. Okay. So this theorem is proved now. Okay. Now we will do one example on it. Example. GLNR with matrix multiplication is a group. So that SLNR is SLNR. We have done same question, okay? So we are doing now by today's theorem. We already discussed this in previous lecture. This is subgroup of GLNR. Proof or solution, you can say. So IN belongs to SLNR. Okay. So this implies SLNR is non-empty. And SLNR is subset of GLNR. Now let AB belongs to SLNR. Okay. Then AB belongs to M and R, and determinant of A is 1, determinant of B is 1. Now AB inverse belongs to M and R. Okay. And what is the determinant of AB inverse? It is nothing but determinant of A, determinant of B inverse. So this is determinant of A, and what is this? This is 1 upon determinant of B. So determinant of A and B is 1. So we put the value, that is 1. So this implies AB inverse belongs to M and R, and determinant of A, B inverse is 1. So what is the meaning of this statement? What is the meaning of this statement? The meaning of this statement is AB inverse belongs to SL and R. Okay. So this implies AB inverse belongs to SL R for all AB belongs to SL and R. So this implies SL and R is a subgroup of GL and R. Okay. So prove. Okay. So today's lecture up to this. If you have any problem related to this, you can comment on my YouTube channel. Like, share, comment and subscribe my YouTube channel. So thank you very much for today's lecture. Thank you.